Hi, my name is Brandon Gracely. I'm a high school math teacher. We're going to learn about how the sine law works for obtuse triangles, and we're going to learn about the ambiguous case. Now, the word ambiguous means that the answer is uncertain. There's more than one possibility, and so that's going to come up as we move through this, that we can have more than one answer to a single question. So here I've drawn a triangle, and it has side lengths 15.1 and 9.5, and we don't know this side length. And we do know this angle over here, 32 degrees. So across from this angle opposite, we have this side length 9.5, and we know another side. So that means that we could use the sine law to find the other opposite angle, the angle at vertex C. So that's what we're going to try to do. We're going to try to find angle C. And we are going to run into a problem in just a moment. We're going to go through, we're going to solve it using sine law normally, but then we're going to notice the problem that has happened at the end. So let's start by setting up the sine law. Because I'm finding angle C, I'm going to start by writing down sine of angle C, and we divide by the side length opposite, 15.1. We set up the ratio for A and A, so sine A is the sine of 32 degrees, and side length A is 9.5. Okay, let's just rearrange this. Sine of C is 15.1 times the sine of 32 degrees divided by 9.5. Now when I'm working on something like this, I like to write down a decimal approximation just to make sure I've typed everything in correctly and I get something reasonable. So 15.1 times the sine of 32, and that's divided by 9.5. So about 0.8423. I'll leave that value on my calculator though. I'm not going to type this number in again. Now let's find the sine inverse of about that number. I just want to point out I'm not writing C equals here because we are going to need to be more careful than that. I've left it on my calculator. On this calculator I press shift and then the sine function, that gives me the sine inverse. Press the answer key, that's the previous answer. And I've got about 57.4 degrees. Okay, and so, looking at my diagram here, that seems reasonable. 57.4 seems to make sense. So that is a possible solution. Let's write that down. One solution is that angle C is approximately 57.4 degrees, and that is true. However, this is where we're going to have another issue. So, but between 90 degrees and 180 degrees, there is another solution. That would be an obtuse angle. And I'm just going to say in brackets here, which is the related angle in quadrant 2, Q2. Now, if you don't know about related angles yet, you should back up and look at that first, because you need to understand that to know how to find this related angle. Okay, so our strategy for finding that is pretty straightforward though. 180 degrees, and we subtract this related acute angle. So we're kind of backing up from 180 by this much. And we get 122.6. Okay, so this is another solution. Let's see what that must look like, because it doesn't seem right in my triangle. Let me just sketch the triangle out again, so I can draw on this one. So we have A, B, C, 15.1, 9.5, and 32 degrees. That's really important. I want you to notice this 9.5 side is quite a bit smaller than 15.1. So what if, instead of drawing it like this, I drew it kind of pointing in the other direction? Same length, still 9.5, and everything else has stayed the same. This is still 32, this is still 15.1. I've just drawn this differently with a shorter side length AC. This is like a different version of where C could be in the diagram. And this would give me the obtuse angle 122.6. the other angle that we figured out, the acute one, was 57.4. That's sort of that's what it would look like if we had an acute triangle like this, or rather an acute angle for C. So the truth is there are two answers. There are two different ways to solve this triangle. Let me just go back up to my beginning triangle. I drew it this way, but there are really only three pieces of information. And I was kind of guessing about what the triangle might look like. So there are two answers. This is what is called the ambiguous case. And now we're going to go through some rules about how this can happen. So the ambiguous case has essentially two rules that we have to look at. So the first rule is you have to know one acute angle and two sides. Okay, and because we're using a sine law case, that one of those sides has to be across from or opposite from that acute angle. And the other thing is the shorter known side, one of them has to be shorter. That shorter known side has to be part of the known side angle pair. So the shorter known side has to be part of the known side angle pair. Now that's a fancy way of saying it's across from the acute angle. So the short side is across from the acute angle in our sine law situation. So let's draw another situation just like that, and we'll see once again that we have two answers. So I'm just going to draw a triangle here. Maybe the angles won't feel that good, but there's 43 degrees. Let's make this one 20, and this one over here is a little bit smaller at 17. We'll give it a label, I suppose, D, E, F. All right, so let's see. We have to know one angle, it's acute, and we know two sides, yes. And the shorter of the two sides, 17, is part of the known side angle pair. We know this side and this angle, that's the known pair. We don't know F, we don't know D. Let's set up our sine law situation. Maybe I'll write down the sine law kind of formula first. Here it's the angle F that is the kind of the concern. Sine of F divided by side F, which is 20, is sine of angle E divided by side E. Notice we use capitals for the vertexes for the angles, and for the side lengths that are opposite, we use the same lowercase letter. Sine of F divided by 20 is sine of 43 divided by 17. Rearranging, sine F is 20 times the sine of 43 divided by 17. I'll write down an approximation. It's not strictly necessary, but I find it helpful. About 0.8024. Now we'll work on using the sine inverse of that value. You can also just type in your long expression here inside of your sine inverse function. Shift, sine, use the answer key, about 53.4. Okay, so now here's how we continue. The quadrant 1 solution is 53.4 degrees. Or rather, I should say angle F is 53.4 degrees. For the quadrant 2 solution, we know there is one because this is the ambiguous case. Angle F is the related angle in quadrant 2. So it's 180 degrees minus that value, which is 126.6 degrees. Okay, so once again, we have the correct situation, two sides and an acute angle, and the short side is the one across from the acute angle. We are going to get two answers if we get any. We go through, we found an answer, then we can find the other answer. So you have to understand, though, that this does not always happen. So there are a few things that can keep us from having an ambiguous case, which is nice. So one possibility is that you end up with a side length that is shorter over here, one of these adjacent sides, if you like, the ones touching the angle that you know. If that's the shorter side, no go. That's not an ambiguous case, essentially because there's no way for this 50 line to flip around into here. It doesn't fit. So this is too big. Okay, let's look at another problem that can happen. I call it a problem, but it's kind of nice when there's no ambiguous case. Well, what if we have something like this? This is actually going to have two problems. This has the same problem of the opposite known side being so much bigger than 8, but this is not acute. It has to be an acute angle, otherwise you couldn't possibly fit another obtuse angle inside the triangle. There can only be one because a triangle's angles add up to 180. Let's have another possibility here. Now this one will be less obvious, so this is the one to kind of watch for, I suppose. It's not hard to detect it, but you do have to do a little bit of math to find your way there. Let's say that's 75, and this is 17, and that's 20. Very similar to the one we looked at before. But this one seems like maybe it is an ambiguous case. We have 75, that's acute, just barely. 17 is small compared to 20, and that would mean that this angle over here could possibly have two answers. Let's get started into it, though, and we'll discover that there's a different kind of problem that can occur. So you can't see this yet, not until you begin. Sine theta divided by 20 is sine 75 over 17. We start rearranging. 20 times sine 75 over 17. Let's do the approximation, and you'll see right now why I like to do this. Sine 75, and then divided by 17. Okay, well I got this crazy looking thing. Let's turn it into a decimal approximation. 1.1364. I know some of you just thought, wait a second, that seems weird, and it does seem weird because sine always gives a number between 0 and 1. If you think back to the unit circle, you'll see that it's always something between, well, I should say -1 and +1, but it's never something large like this. Essentially, that means this is not going to be possible to solve. Maybe you didn't notice that, though, so let's try finding the sine inverse of that number. Grab the calculator, shift, sine inverse. The last answer is a math error. Wah, wah. So that is not possible. Now, our technical way to say this is that sine theta equals this has no solution. And what we can say as a result is, therefore, theta does not exist. That means essentially that this triangle, a triangle with these given measurements, is not possible. There is no triangle with 75 degrees, 17, and 20 like that. It doesn't exist. It just can't fit. Now you might be wondering, what about the cosine law? Is there an ambiguous case there as well, the same as there is for the sine law? And thankfully there isn't, but there is one small thing to be careful of, and so I'm going to show that to you right now. So let's draw a triangle. And let's call it A, B, C. I'm going to give you some side lengths, but I'm not going to give you an angle. And so if we need to solve this triangle, solve triangle ABC, we usually go through the following steps. We use cosine law to find an angle. Once we know an angle, we have an opposite side angle pair, and then we use the sine law. Oh, I'm sorry, I forgot the word law. Use the sine law to find another angle. And once we have two angles, we can use the sum of the angles in a triangle theorem, that's the 180-degree thing, to find the last angle. All right, that strategy is still great, but there is a small problem. The problem is this: if you find an acute angle first, like this one, then when you go to use the sine law, you'll have an acute angle, a short side, and a long side. That's the ambiguous case of the sine law. We don't like that very much. However, if you instead choose the largest side, in this case like vertex A and the long side 16 here, then you won't have the ambiguous case when you go to step 2 of the sine law, because this is a long side. What we're trying to do is avoid having the sine law's ambiguous case show up. So we don't want to find C, we want to find A. So we're going to make a little modification. Instead of using the cosine law to find an angle, we're going to say use cosine law to find the largest angle. And if that angle happens to be obtuse, we're going to find it out right away. The cosine law can reliably find any one of these angles. In fact, you could use the cosine law 3 times if you really wanted to find all the angles, but it's a little more labor intensive than the sine law. So this is the strategy we usually use because it's faster. Okay, let's go ahead and use the cosine law to find the largest angle. So angle A is the one we're going to find. I set up the cosine law like this. A squared, that's side length 16, is b squared plus c squared minus 2bc times the cosine of A. You might also know how to just write this out with cosine of A equals some stuff, just a rearranged version of this. Maybe I'll do that for you right now. So some people memorize this in both ways. This would be a squared minus b squared minus c squared divided by negative 2bc, or you might have that negative sign out front there. Any of those is fine. So a is 16, so we'll do 16 squared. B is 12, 12 squared. C is 6, 6 squared. Negative 2 times 12 times 6. Okay, so you can probably just grab a calculator at this point, but I can do some of these in my noodle. That's negative 144. I've seen students try to cancel stuff in here. Don't do that. Simplify the top, simplify the bottom. There is no canceling, no such thing here. All right, let's grab a calculator because I could see myself making a boo-boo here, especially on camera. Okay, 76 is on the top, and 144, and it's negative. I'll just put the negative sign up front there. And if you wanted to, you could simplify that, I think, right? Because they're both even. 76 over 144. You could write as negative 19 over 36. It's not exactly necessary to do all this. In the end, we're going to use the following. Cos inverse of negative 19 over 36, or this one if you want, same thing. So, cosine inverse, negative 19 over 36. And look, I get that obtuse angle, 121.9, let's say. Excellent. So we have our largest angle. It's 121.9. And we can go ahead and use the sine law and then the sum of the angles in the triangle theorem to find the remaining angles. Okay, let's do that now. We know this angle, so let's find either B or C. It doesn't really matter now because they both have to be acute. They're both smaller than this one. So let's find b, I suppose. So that means I'm going to write down what I'm looking for first. Sine b on the top, b on the bottom, that's 12. And then I have to use a and little a. So sine 121.9 degrees divided by 16. So sine b is 12 times the sine of that angle divided by 16. I'm going to put an approximately dot there because this is an approximation. Now I do still have that value on my calculator, so there's an exact value, kind of, stored at least. So I'm going to do the sine of that, last answer, times the 12 divided by the 16, and I get about 0.6370. Okay, let's do sine inverse. And it really will be angle B now because I know that I'm going to get an acute angle. So sine inverse of this, 39.6. All right, we are almost there, and that is angle B. Okay, and angle C then, we need the sum of the, let me write that in the triangle, I suppose, 39.6. And for angle C, we just kind of have to add everything up. We know that angle C will be equal to 180 minus the other two, 121.9, and also 39.6 approximately. So angle C is about, what's that, 18.5 degrees. And so we can write that in our triangle as well. Okay, and now we have finished solving the triangle. Quick recap then, cosine law, same as always. The only special situation you have to worry about is that it's possible that you may set yourself up for an ambiguous case accidentally. So be careful to find the largest angle first so that you don't have a sine law ambiguous case that might cause problems in your second step. You can also use cosine law twice. That will guarantee that you always get the right answers. And if you're not sure about the sine law's ambiguous case, go ahead and use cosine law 2 times before you use the sum of the angles in a triangle theorem. Okay, I hope that is helpful. If you have any questions, of course, go ahead and ask. Thanks.